at this, if you look at this beautiful coastal waters of Dubai, you can see the infrastructure importance of the coastal waters. But behind that, we can also think about the importance of these coastal waters. So basically, the coastal areas here, they are a significant source of food, especially for the countries that has a long coastal border like the UAE, where maybe more than 40 to 50% of the border of the UAE are in the lying on the Arabian Gulf and also the Sea of Oman. The other thing is that these coastal areas, they are also significant source of water. So the water quality is also important to be monitored, especially in this region where we have a shortage of freshwater resources and also the reliance on the desalination plant. The third thing also I would like to touch on is the tourism and entertainment. So for example, here you can look at the Burj Al Arab and how much tourists could be attracted to these areas. So by maintaining the quality of the water, in this case, we are also maintaining the economy sector of the country that is heavily dependent on the coastal tourism. So all of these factor has emphasis on the monitoring plans for the coastal areas and how can we maintain the quality of the water. So if we think about the the quality of the coastal water, we can think about different parameters. So there are different satellite-derived coastal water quality parameters that we can look at and we can monitor to maintain the quality of the water. Among the long list of the water quality parameter, I'm listing here the 5 most commonly monitored parameters based on the remote sensing and the satellite. So the first one is the chlorophyll A. So the chlorophyll A is a proxy of the water productivity, for example, the phytoplankton and algal growth in the seas. So it could be estimated by the concentration of chlorophyll A, which is measured basically by a microgram per liter or milligram per meter cubic. And this chlorophyll concentration, if it exceeds a certain amount, like 5 mg per meter cubic, which means that there is high productivity in the sea, which sometimes is not good because it consumes a lot of oxygen and it causes some outbreak like killing the fish and also the other mammals in the sea. The other proxy for the water quality could be the fluorescence. So the fluorescence is how much is fluorescence being out of this phytoplankton, and it could be modeled based on the satellite and remote sensing. The second parameter for water quality could be the turbidity. So the turbidity refers to the sediments, suspended sediments in the water. So as you can see here so in this, for example, water surface, so the turbidity here is higher compared to this one, and it could be derived by the satellite using the KD, which is the attenuation coefficient. So if the attenuation coefficient is high, it means that we have less turbidity, and if it is low, we have a high turbidity, because the attenuation coefficient basically is the depth where the light can penetrate into the water. The third water quality parameter could be the color dissolved organic matter, and it is a problematic one because it also gets distinguished with the chlorophyll A in the case 2 water especially. The fourth one is the salinity, and salinity could be modeled based on the microwave bands, and this is common in the satellite like SMOS and SMAB. And the last, not the least, is the sea surface temperature, which is the focus of today's presentation. So this is one of the important and most commonly used parameter to define water quality of the water. So the focus today, as I mentioned, is only on the sea surface temperature and the uncertainties of the sea surface temperature at the coastal areas. So first we need to define the sea surface temperature. So the sea surface temperature is the water temperature close to the ocean's surface. And here when we refer to the surface, so the surface basically varies according to the measurement method. So the surface could be between 1 millimeter, which is 0.04 inch, to 20 meters, which is 70 feet below the sea surface. In another reference, they define the sea surface temperature as the ocean depth of 20 to 30 centimeter. So the top layer of between 20 to 30 centimeter will be representing the sea surface temperature in this case. And the sea surface temperature is important and could be modified by the air masses in the Earth's atmosphere. So if we have high heat flux, the sea surface temperature can also affect the heat flux. So in this case, especially for the ocean models, they use coupled models, because coupled models they capture the effect of not only the air temperature on the sea, but also the effect of the sea surface temperature back into the atmosphere. And for example, warm sea surface temperature, they are also known to cause some cyclone events. So this make the sea surface temperature is an important parameter to be studied. So again, why the sea surface temperature and why I have chosen this parameter for today's presentation, because it is a strong indicator of productivity. So the changes of the surface temperature might change the mixing and the circulation of the water column. And by doing this, you are changing the biochemistry of the water by changing the position of the nutrients and improving, for example, the upwelling events sometimes in some of the oceans. Thus, the productivity might also increase. Also, the sea surface temperature might be preferable for some of the phytoplankton, so they prefer to live in particular sea surface temperature. So the changes of the temperature can improve the environment for these phytoplankton to grow. The other thing is a strong indicator of pollution. So nowadays, the pollution and anthropogenic activities can increase the temperature of the sea. So by studying the sea surface temperature, especially for the long term, it will obviously help us to define the hotspot of the pollutions and how can we tackle this pollution and hotspot area. The last one, the sea surface temperature, of course, is important to study the global climate change, especially nowadays now. So the satellite era started in 1970s. So by now, at least we have 5 decades of satellite products. So by having a time series or analyzing all of these 5 decadal data, then we can create kind of climate change trend and understanding the decadal and also the climate change effect on the temperature. But it's very tricky because we need first to sort out the uncertainties of the sea surface temperature itself before deriving conclusion for the climate change. Thus, the SST has been measured in the past, and the sampling of SST started from the ships, basically. So the instrumental SST has been measured on ships at the ocean surface for more than 200 years. So by now, we can have more than 130 million ship-based measurements since 1850s. And if you can see here in the map, so here are the efforts that have been done in the past till now, of course, to collect the sea surface temperature based on the ships. But as you can see, most of the efforts being done in the coastal areas, and of course some transaction to move from one side to the other side. And since 1970s, we have an increasing number of ships and with specialized digital sensors. And this has created really long-term and long-established records of the sea surface temperature. We can also see that there were like kind of improvement in the sampling technology. So at the beginning, they have try different type of buckets, as you can see here, starting from 1890 till 1990s, and after that we can see they have started the drifters and mooring sensors to collect the sea surface temperature. So all of these could also add uncertainties to the SST estimation. In addition to that, we have also the drifters and the argo floats. So nowadays, argo floats are all over the ocean, like more than 4,000 argo floats, providing sea surface temperature and also the temperature of the water column all over the world. And as you can see here, also we have the buoy. So we have also the buoy SST observation being also measured in the global ocean. So this is regarding sampling the sea surface temperature based on the in situ and based on the field observations. However, if we think about the satellites, so the same thing, efforts have been done to model the sea surface temperature using the satellite, thanks to the development of the sensor and also the improvement in the spectral resolution and the spectral capabilities of the sensor, especially focusing on the thermal bands. So thus the SST from satellite and other sensor became available in 1980s when these thermal bands have been developed. As you can see here in the figure, different types of sensor could map the SST. However, the satellite basically observed the skin temperature. They call it the skin temperature is only at the upper millimeter of the surface, unlike the other in situ instruments. So regarding the satellite estimates of the sea surface temperature, there are mainly two approaches. So the first one is the multi-channel SST approach, which is basically depending on two bands of thermal wavelengths. So as you can see here in the equation, so TS, which is the sea surface temperature, is a function of the brightness temperature, sorry, in various bands, basically in two bands, and these two bands are the thermal bands, and the coefficients here, alpha, beta, and gamma, give the parameterized correction. So basically they are just parameters that have been estimated based on the sea surface temperature of the observation. An example of this approach being implemented in the Aster satellite using band 13 and band 14. And sorry, as you can see here, the wavelength between 10.25 to 1095, the same thing for 14, 1095 and 1165 micrometer. So this is the first approach to estimate the SST. The second approach is the nonlinear SST approach, NLSST. In this function, basically they add the zenith angle into the equation and also addition scan angle coefficient. So the same thing, you have two brightness temperatures, but here you can see the scan angle being added and the zenith angle being also added. This approach being implemented in satellites like the moderate resolution imaging spectral radiometer, which is MODIS, and also the advanced very high resolution radiometer, the AVHRR. Okay, so based on this, basically these satellites have been given different accuracies. However, to use the SST for climate change effect, we need to have the accuracy around 0.3 Kelvin. In another reference, it should be an accuracy of 0.05 at the global scale and 0.1 at the regional scale to study climate change. The other thing is that SST accuracy is important because the SST will be used, for example, at the boundary condition to run the numerical model and to produce, for example, the variability of the meteorological phenomena. So the high accuracy of the SST is required. So if we look at the past and we look at the studies that have compared the SST derived by the satellite with the in situ data, we could see some uncertainties. For example, here, the first studies that have been done in the Mediterranean, for example, Sea, they have compared the AVHRR and MODIS SST during 2 seasons, the summer season and the winter season. So they found that the bias during the cold month around 0.09 degrees centigrade with a standard deviation of 0.1. However, the bias has increased to 0.24 during the warmer months, which is during the summer season, with a standard deviation of 0.2. The other study being done in South China, and they have used MODIS SST compared to the in situ data, and they found that the bias is between minus 0.19 to minus 0.34. And relatively, the smaller bias is also observed during the winter season, but during the summer season, the bias also is increased. In the Great Lakes, they have also compared the MODIS SST with the in situ measurement, and they found a bias of 1.5 during the summer season, and this is because of the effect of the fog. So the Great Lakes, they have foggy environments during the summer season, thus the bias has increased during the summer season, which is 1.5. So in this case, you cannot study climate change effect in such a high bias records of SST. The fourth study is at the South Africa coast, and they have compared the MODIS SST with the in situ measurement at the coastal line, as you can see here, of South Africa, and during different seasons, and they found that the highest bias could reach up to 6 degrees, which is the highest among all the studies, and this could be caused by the coastal sedimentation and also the high turbidity of SST. So to continue the efforts of comparing the SST and doing kind of assessment of SST with the satellite, so the objective is just to quantify the error of SST satellite in relation with the water depth, turbidity, temperature, dust level, wind speed, and solar angle. And in this presentation, I'm showing you a case study for only the Arabian Gulf. So based on the in situ data collected at different cruises along the UAE, considering Masdar station, the cruise station of Muscat, and also shallow water station, we have collected SST measurement at this region for different years and also different seasons. And we want to compare these in situ measurement with the MODIS SST, and we see the uncertainties of MODIS compared to these coastal areas, and we will interpret the uncertainties with the parameters that I have just shown. Before going to the satellite, so first we want to check the variability of the in situ SST in the region, in addition to the change of air temperature and wind speed. So starting with the SST, as you can see here in the first column, so the sea surface temperature, based on the data that I showed in the previous slide, the average is 33.5 during summer season with standard deviation of 1.98. However, in the winter, the average become 27.65 with standard deviation of 2.93, which is more than the summer season. And the maximum temperature can reach 39.4 during summer, while in winter 34. Regarding the air temperature has an average of 35.79 during summer with standard deviation of 2.9. However, less air temperature, of course, during the winter season with average of 28 and standard deviation almost the same with the summer season, which is 3. Regarding the wind speed, not significant changes in terms of the values, but we can see the variability is different between the summer and the winter. So during the summer, the average is 2.79 meter per second with standard deviation of 1.67, while in the winter, almost the same average, but we can see here the values have been fluctuated between 2 to 4 during the winter season. So moving to the MODIS SST, we have just got the level 3 SST data obtained from NASA Ocean Color website, and in this website they derive the level 2 data from level 1A, considering the geolocation, level 1B, and then applying the atmospheric correction and applying also the flags, for example, the sun glint flag and the other flags, and then to get you the MODIS SST with a resolution of 4 kilometer. So we try to compare MODIS SST with the NC2 SST, and here you can see the matchup between MODIS SST and real SST. The total observation is 450, and R square is 0.88. So if you think about it, R square compared, to the statistic point of view is very, very high, close to 0.9. But if we think about the climate change need of this data, we will think that still the data needs to be improved, especially, for example, here, when the real data shows 26, we can see here the model showing, for example, 30. However, most of the data have been located at the 1-1 agreement line. So if we look at the bias in both the winter and the summer season, just to understand the highest bias could observe in which season. So during the summer, the average bias was found to be around 1.04 with standard deviation of 2.04, while in the winter, the bias has an average of 0.77 and standard deviation of 0.99. So this makes these results convenient with the studies that I have shown, that in the summer season, they found that the uncertainties and the error in the SST is higher compared to the winter season at the coastal areas. So if we try to understand the biases compared to the parameters that we have collected during these sampling. So for example, the bias compared with the wind speed, so we see that the bias has kind of not clear relation with the wind speed. So some of the higher wind speed contain less bias, and also here, and some contain high bias. So wind speed could not be a direct effect causing this bias. However, if we compare the bias with the air temperature, we see that there is kind of linear relation between the bias and the air temperature. So as the air temperature increase, we can see here there is an increase bias in the estimated MODIS. If we compare the changes or the bias with the water depth, we could see that at the higher depth, so this is the water depth means the bathymetry. So at the highest bathymetry, we can see that the bias doesn't exceed, for example, 2, but at the lower bathymetry, lower than 10, we can see that there is a potential of higher bias, which could say that the low bathymetry can affect the estimates of the satellite and cause a significant bias over here. Here we consider the turbidity, which is SSD over water depth, and we could see here not really direct correlation between the bias and the SSD over water depth. So regarding the instantaneous effect, if we look at specific, for example, of the bias regarding the parameter that we have seen here, for example, here we plot only the changes over the 52 station that we have. For example, at 0.5, we can see there is a reduction in the SST. There is an instantaneous reduction in SST, which is also corresponding to also the reduction in the air the air temperature, for example. However, in some areas where the depth, for example, here is high, this is the water depth, but still we can see there is a decrease in the temperature. So sometimes the depth might not be the cause in some instantaneous places. So it seems that the problem is more complex, and it is a multi effect of different parameters on the estimation of the SST. So if we think about the atmospheric effects, so as I mentioned that in the Great Lakes, they have found that the fog could affect the estimates. So if we compare the bias with the aerosol optical thickness, and during these campaigns, during these days of the station, so we could see that there is not really clear correlation between the bias and the AOT. So referring to another study being done before, they mentioned that the bias could be caused by the AOT if AOT exceed 0.3. However, based on the field campaign data, the maximum AOT was 0.3, so we could not get the result or see the impact after 0.3. So to check the impact, we tried to get a case study. For example, here there was a massive dust storm happened in 2019 in July, and mostly you see the dust covering the southern UAE and also part of the Sea of Oman. So we try to look at the sea surface temperature that has been estimated during this dust storm, even since we don't have yet the in situ data. So the corresponding SST image, you can see here at this particular place where there was a like high dust concentration, we can see that the SST could decrease compared to the other surrounding region. So does this been affected by the dust effect, and this cause an error in the estimation of this SST, yes or no? So we try to check the reflectance and emissivity of these different places. So we try to look at the reflectance and emissivity at the dust over the water, the center of the Gulf, and also at the northern part. So comparing the three different locations, we can see here the dust has increased the estimation of the reflectance between 500 to 2000 nanometer. However, in the emissivity, which is the thermal part, so this part is used for the SST estimation, we can see that the purple spectrum is less than the blue and the green, which can cause a bias in the SST estimation by lowering down the emissivity. And based on the equation, we need to get these values to estimate the SST. So does the dust, the high dust storms like exceeding 0.3 AOT could affect the SST? It might be the case depending on this example, but of course more studies needed to confirm this hypothesis. So at the end, if we want also to check the variability of the SST at regional scale, not really at these field stations. So we mapped the SST for the 12 months between January to December, and also we mapped the wind speed and later on I will show you the zenith angle and the azimuth angle. So first, if we look at the SST distribution, so during, for example, the month of January, you can see here there are almost 4 kind of classes: high SST in the Sea of Oman, lower inside the Gulf, and it's getting lower as you go to the northern part toward Kuwait. The same thing, the same pattern being observed in February and March. However, the opposite happened during the summer season. So during the summer season, the Sea of Oman show colder water sea temperature compared to the inside of the Gulf, because of the increase in the temperature inside the Gulf during the summer season. So comparing the coastal area with the basin-wide area, So here, if we see the coastal area, basically they follow almost the same temperature of the basin wide. So the coastal area doesn't really get a lot of uncertainties compared to the basin wide in most of the area, except the coastal area here near Qatar is always overestimating the temperature. However, the satellite is doing well here. The MODS SST is doing well in terms of the deriving the SST at the coastal area. So comparing this with the wind speed, so we noticed that colder SST is corresponding to lower wind speed, and all the wind speed comes from the north to the toward the Sea of Oman. Thus, you can see these changes in the sea surface temperature. So the major effect of wind speed also is observed at the northern part, but the Sea of Oman is less affected by the wind speed. So the wind speed could affect also this gradual changes of the sea surface temperature inside the Gulf. So if we compare the SST with the solar azimuth angle, so we derive the solar azimuth angle from MODIS for the 12 months, and you can see here the variability of the solar azimuth angle during the month. So the lower is at the southern part and high at the northern part. So one could tell that okay, the high solar azimuth angle can cause a lower sea surface temperature. This could be the case, but if we look at the zenith angle, we could see like higher correlation between the solar zenith angle and the SST. So for example, here the solar zenith angle is around 48 at the south, 53 at the north, and you can see the distinct variability from the south to the north, which is convenient with the changes of the sea surface temperature from the south to the north. It doesn't make sense, yes, because MODIS SST basically uses the solar zenith angle in the equation, but here it's good to see the variability in terms of the seasonal changes of the solar zenith angle and the sea surface temperature. However, this is very obvious during the winter season, but the effect of the solar zenith angle is less during the summer season. So you can see there are kind of uniform distribution of the solar zenith angle during the summer. So this might not be the case of changing the SST, and the dominant effect of SST could be the air temperature or the heat flux from the atmosphere. Yeah, I think with this, I reached the final conclusions of this pre-assessment of SST in the region. There are uncertainties in satellite estimate of global SST when compared with the in situ data. So several regions, including the Mediterranean, South Africa, have reported these uncertainties where SST residual can reach up to 6 degrees, especially in the South Africa. So results show that high SST bias is most likely caused by high air temperature because the bias is higher during the summer season. So the shallow water depth and bottom reflectance intervention can significantly affect the estimation of SST. So as we can see in the comparison, the water depth or the bathymetry, when it is lower than 30 meters, you can see the bias is high. So due to the effect of dust or long wave radiation, and there was like reduction in the emissivity in the thermal bands, so SST could be underestimated during the extreme dust events, and this could be examined more with the in situ data. Yeah, so this will bring me to the end of my presentation. Thank you all, and please let me know if you have any question.
Thank you so much, Dr. Maryam, for your presentation. It was very interesting and informative. We will leave the floor now for our audience to ask questions. Kindly raise your hands if you have any questions. And if you want to discuss anything, please feel free to send your questions and inquiries in the chat. So I don't think there is any questions. Okay, I think we can end our webinar. So we finally came to the end of this webinar. Oh, okay, there's a question right here. So one question is, overall, the natural variability is far smaller than the bias. This is a question from Jonathan.
In conclusion, overall, the natural variability is far smaller than the bias. I don't get the question. Sorry if.
Jonathan, if you can rewrite the question, maybe. The natural variability is smaller than the bias. I'm not sure. Okay, so I think if there's, okay, so you just sent.
Yeah, yes, yes, that's true. So the natural variability is less than 1 degree, and the bias can be 6 degrees. And to study climate change, these biases should be corrected, especially at the coastal areas.
Okay, so I don't think we have any more questions. So
yeah,
we
so
finally.
So if you have more questions or you are interested to learn more about this, you can connect me to the email. So if you go to Khalifa University website, and my email address is there, so you can just email me if you have any other question.
Sure, doctor. How far the uncertainty of using the SST data in climate change?
Yeah, so basically the uncertainties at the coastal areas here, it could reach up to 6 degrees. So to study climate change, these uncertainties should be sorted first.
Okay, so I think no one has any more questions. So we came to the end of this webinar. Thank you all for your kind interest in attending this webinar, and looking forward to meet you in our upcoming events. Have a nice day. Thank you so much, Dr. MARYAM.
Thank you all.
Thank you. Have a nice day. Bye.